class. I had one person say I didn't like it because I didn't go to class often enough and I relied too much on the course echo. Was that you?
I don't need to go. 7 o'clock at night. Just watch it.
Yeah, but I think it's helpful to be live and in person. I had a couple of frantic emails about the first midterm, and I guess I need to say that we have to get through enough tough stuff to have a midterm, and that's going to be closer to the end of October. So we have it's a month off, maybe 3.5 weeks off. So I wouldn't worry too much about it. The format, just so you know, I think I've said this again. It'll be closed notes, closed books, no calculator in the room, full period. What did I say? Was it worth 30 points? I think it's worth 30 points, and it'll be 3 questions. Okay, and it'll cover whatever the course we've done so far. Okay. Pardon? Oh yeah, I still haven't decided about that. Give me till Wednesday. I want to make one small change on the document, and then I'll assign it officially. But you can go ahead and download the document now off of my webpage and get a sense of what it is. Well, so that's going to be handled a little differently. I'm going to assign the project, but I'm not going to collect it, and those are the changes that I kind of want to make on the document. But I will. Our last day of class will be a test, and it'll be a test of the homework and the project in class as well. So you'll answer a question about it to make sure that you've done the work. Okay. So it's very different from what I've done in the past, and the reason for that is quite simple. I had a lot of plagiarism on the project in the past, and that's not fair to anybody, because I don't know who's plagiarizing, and so the folks that do it themselves and work hard, they may get a lesser grade than someone who copied, and that's not fair. And so I've had to change things around. For your interest, next year I'll change books, and the book will have a much different view of computational electromagnetics, and so I'll be able to get rid of the project altogether. I was going to try to get that done this year, but I didn't hear back from some of my colleagues in time, so I didn't. I was lazy and I kept with the same thing. Okay? Too much information.
You're okay? You're discussing our stuff?
Absolutely. In fact, I encourage it. And even when I did the project, I encouraged people doing teams of 2 and 3 for exactly that reason. And I also do that with homework as well. I don't know how you like to do it, but I used to try doing the homework by myself, and then I would invariably have to learn from somebody else. And so it was by working together, you walk out with much richer understanding of the problem, and that's really what I'm after. Okay, so I don't mind the overlap of work, and then I test for it. I'll test for it with a closed notes, closed book, no calculator test of problems. But if you've done it well, that won't be a problem at all. It'll be an easy, 30 points on your grade. You'll show up, you'll do it, and it'll be cake. So it's not supposed to be. It won't be a surprise what's on the test. Okay. All right. I know it's a weird way to do it, but it's worked in undergraduate classes for a while, pretty well. So, okay. Well, let's see. First of all, how was lectures last week? Okay. I have a very diplomatic class. Remind me not to ask anybody how my lectures go. I'll get the same polite smile and no answer. But we're fine with that, actually. We can live with that. I promised a couple of things at the beginning of the course. I promised that we would talk about all the elements, all the fields of the that we're interested in, and we've done that. We've looked at E, H, D, B, J, rho, V, A, F, the force, S, the pointing vector. We looked at material properties, which is capital M and capital P, the magnetization and the polarization. Am I missing anything? Not so much. I think that's all the fields, right? That's everything you'll ever see in this course, and in a lot of courses of EMAG actually. So it's fairly comprehensive list. There are a few other potentials out there that work that are nice in different instances, and there's a few other little tricks here or there. But by and large, that's let's say 95% of EMAG, and it covers a lot. The other thing we did was we looked at materials, and in fact, TJ's lecture from last Monday was also a very important material problem, the electron on a spring or the plasma frequency. Nice driven, simple harmonic oscillator, giving you nice responses, curve responses. That's a really good model to look at for more problems than you would care to think. We also decided that, I gave some instances in the past of starting with Maxwell's equations and kicking them around to pull out information. And in some instances, you would solve those differential equations. Well, we're going to derive and solve our a wave equation tonight and on Wednesday. So we're going to start with Maxwell's equations tonight. We're going to take derivatives of them. We're going to make some substitutions for them. We're going to get them into a form that we'll call a wave equation, a second derivative of space, a second derivative of time. And then we'll look at some very simple solutions to those equations, and we'll present that rather classically from a partial differential equation perspective. Okay? And I'll tell you how to look at it in other ways as well, but I'll probably be more hand-waving on that. So let's start with your favorite Maxwell's equation.
Curl of H is...
Oh, thank you.
Yeah, I know you're being crazy.
No, I don't mind it. I love all my I love all of Maxwell's equations equally. Well, at least, for the amount of information that they give.
Yeah,
So the curl of H.
D.
Good.
D, T,
Good.
plus J.
Good. Good. So the coupling to the electric field in a time-varying sense, and the forcing term due to the current element. This is the antenna term, the broadcast antenna term, the way I look at it. And then that shapes the curl of H. Do you want to give me the curl of E equation? Yeah.
The curl of B, no, the curl of E equals minus delta B.
Good. 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 And you can look up here for inspiration, right? E and H go together, and D and B go together. Right? So there's kind of a nice symmetry there. And because there's no north poles alone, we don't really have a current flow there. There was a question I think that somebody asked by email to me. And in the physical world that we live in, that we appear to live in, there is no extra term here at all. Although your textbook and many other textbooks like to brag and like to show off a little bit and put in a what-if term there. And I like that because it kind of there's kind of a story there of a broken symmetry somewhere in the history of the universe. It seems to me that there should have started out with symmetry, and then maybe because of the Higgs boson or something like that, or some flow of energy, the Big Bang condensed into a manner that was a little funny. You're very smart also to note the minus sign there, that this is in old-fashioned terms, that's the back EMF. It makes your motors work a little bit harder. And what it does from a mathematical perspective is it keeps the entire set of equations stable. And so we get complex exponentials instead of exponentials, or we get sines and cosines instead of hyperbolic sines and cosines. And so we have oscillatory behavior instead of diverging exponential behavior. And that's generally good for an existence of life, if things are staying sort of around some bounded input, bounded output sense. So that's kind of nice. All right, now let's take care of the other two equations. I never bug that side of the room. They go to sleep because they're so far away from the podium. So I have to shout.
The divergence of B.
you say B or D?
B
B.
equals 0.
Good. No magnetic monopoles to force that equation. And then the last one, divergence of D. Again, B and D go together. D and B go together. And that's just charge. So I've got two forcing terms. Charges get an electric field. No monopoles. Coupling terms, another forcing term, and the shape terms on E and H. Okay, and then for grins, we're going to look at material relations, and just to be blunt, we're going to mostly have very simple materials. So D will be proportional to E, B will be proportional to H. But let me just sort of remind you, mu naught H plus M and epsilon naught E plus P is the more general expressions. And I may substitute those in and then very quickly get rid of the polarization and the magnetization. And then we also have one more material relation, which was J is equal to sigma E. That's your V equals IR law. So I kind of squint my eyes and wave my hands a little bit, and I say capacitance, inductance, and resistance. You know, so that's sort of a hint at where we're going, right? We're getting a sort of a capacitive term, an inductive term, and a loss term. Eventually, we'll even work with a loss term, but not for a while. Okay. So LC circuits and then LRC circuits, except just generalized into 3 spatial dimensions as well as time. Okay? And then if you think about it, if you're in circuit theory, where you have very, very low frequency approximation or the DC approximation, you don't need to worry about the structures of the electric fields and the magnetic fields. Those are generally constant. The structures will be constant over the size of your circuit. Okay, so if you have a gigahertz signal with a foot and you have a tiny little chip, you know, a handful of millimeters on the side, yeah, the voltage is pretty much equilibrated across the entire chip. If you're at a megahertz, you have 1,000 feet, 300 meters, a third of a kilometer, and you have a circuit board, let's say 16 inches by 16 inches, that's the size of a pretty typical telecom board, then your voltage is basically flat across that. Okay? So again, that's kind of a circuit theory. These should reduce down and account for circuit theory in the limit of 0 frequencies where those guys go away. Okay? All right. So we're going to derive, tonight we're going to derive a wave equation. And just to remind you, our heuristic, our hand-waving, our casual interpretation of a wave equation is that it's a second derivative of space balanced by a second derivative of time. And if you remember the equations that we derived for V and for A, the D'Alembert's equations, those were also wave equations, second derivative with respect to space and second derivative with respect to time. Okay? So this will just be another example of that. Okay, so we'll begin with one of my favorite Maxwell's equations, which is this curl equation. And I want a second derivative with respect to space and a second derivative with respect to time. So the first thing I'll do is try to get that second derivative with respect to space. And so remember, I have this curl of E will give me back a vector. And I have 2 ways of taking the second derivative of a vector field. I can do a dot product, or I can do a cross product with del. We've worked, I think, with the dot product. I believe we did an example of that. So we might as well go ahead and do the other example, which is the curl of E. I have to do this to both sides. Now, notice that I had the curl of minus del b del t, and I interchanged the order of differentiation. So I snuck the del by del t out through the del operator. And I just want to remind you that I can always interchange the order of differentiation. I can always interchange, if I'm taking a second derivative, d by dx, d by dy, I can always interchange the order of differentiation. That's one of those theorems in calculus that you at least memorized if you didn't study. Okay? And so this is a completely general expression so far. Now, this right-hand side in a material I can write B is equal to mu H. Okay? Now, I'm usually really sloppy with my subscripts. You'll notice that I have mu naught H here. This M I would write as a mu naught chi times H, and I would collect all the terms in terms of a mu. So I'm actually in a simple material. Okay? An example of a simple material is mu naught. But this is a little more general than that. Okay, not much, but it's a little more general. Okay? So I use a material relationship there. Now this right-hand side is a chain rule. So I have to take the gradient of mu, cross it with h, and then I have to take the gradient of h and multiply it by mu. So this is the product rule of or a vector identity if you want to look at it that way. Okay? And I'm doing this because remember when you last saw me 10 days ago or so, we went through a large number of material complexities. And so it's quite likely that at some point in your career you'll have a mu or an epsilon that's a function of space, and you'll just have to remember that you have extra terms in there. Okay? But for now, we'll get rid of this, and we need some fancy words to do that. And we'll call that magnetically uniform or magnetically homogeneous. Okay. So I have the curl of V on this side, and then I have d by dt of mu times the curl of h on that side. So what I'm going to do is I'm going to pull the mu through the derivative. I'm just going to say mu is not equal to time. Mu is not a function of time. And I'll have an equation that looks like that. The curl of V is equal to minus mu d by dh of the curl of h. And somewhere, a long time ago, we had some expression that had the curl of h in it. It's a little sarcastic, I apologize. It keeps you on your toes. One of Maxwell's equations was the curl of h. Okay? And if you look at the right-hand side, and you squint your eyes a little bit, you see the right-hand side of that equation is just chock full of electric fields. The D is an electric field, and J, if you like that particular material relation in your problem, also has an electric field in there. Okay? So I can take this curl of H here, and I can substitute del D del T plus J in there. So my right-hand side, whoops. It's not very neat. Now here's my electric field, and I have a material relationship. The simplest thing to do is just to substitute epsilon E in there. But I'm just going to, for fun, for just a few lines, I'm going to substitute this expression in there instead, just to give you a flavor of how these things happen. Okay? So the right-hand side here, notice that the free space will just slide right through the time derivative. We assume that the properties of a vacuum or free space doesn't change with time. I have the polarization term sitting there, and I have the del mu j, and I'm going to use the Ohm's law for that. I can do a lot of different things here, but for now, for this particular run, I'll substitute in j is equal to sigma e for that. Now, if it looks to you like I'm changing my interpretation of j from time to time, then you're very smart. You're exactly right. And so I need to call further attention to that. Okay? So let's back up a little bit. Let's take a break from this and back up a little bit to our starting equations. When I look at these starting equations, I look at j as the antenna term. That's the forcing term. Okay? And in some instances, that's when I'm using these to model a system, and a system has antennas in it, that's exactly how I'm going to do it. Okay? In this particular case, what I'm doing is I'm using this material relationship, this constitutive relationship, which is kind of ad hoc anyway. It's kind of empirical anyway, and I'm putting in a loss term. So I'm using j in this context as a way of bringing in loss into the set of equations. Okay? And so that's a second interpretation of what j is. So I get to interpret how I want to model j, or what j should mean. I have some flexibility on that. It could either be an antenna broadcasting system, a broadcasting set of currents, or it can be a loss term. Okay? Now, if it's a loss term and I want a forcing term, I need to look around this equation and I need to find the forcing term. Any ideas? Very good. It's the only one without an E in it. It took some bravery to say that out loud, but absolutely right. This term here, the P term, is the only thing that's completely unconstrained. And so this can perfectly well be a source term. So if I was just, for example, wanting to model a laser, then the array of atoms or molecules that are excited and that produce a laser field, an electric field, a light field out of the laser, would emanate from this term here. Okay? The losses of that term, scattering and absorption, would come from this term here. Okay? So part of this is there's some ideas behind these terms in terms of interpretation. But you can if you're careful and thoughtful, you can adapt it into the particulars of the problem that you want. Okay? So absolutely right. This could be the forcing term, and this would be the loss term here. Notice just for grins, here's a second derivative with respect to space on this side. Here's a second derivative with respect to time on this side. This is a forcing term, the driving term. And then we have the loss term as the first derivative term. And I think we saw that before when we were looking at a form of the D'Alembert's equation under a slightly different gauge. And I told you about Stokes' law of drag. And so this is another example of a first derivative term. If you go back, and probably most of you remember this off the top of your head, but if you go back to the discussion of an LRC circuit, you won't have anything that changes with respect to space, but you'll have a second derivative with respect to time. You'll have a constant term with respect to time, and if you have a resistor in there, you will, in that particular case, have a first derivative with respect to time, and the proportionality constant will go as 1 over r, or 1 over the conductivity. Okay? So everything, this set of equations should describe circuit theory, and so there's echoes of that in there as well. And it describes more than that, but it certainly describes that, and we can use that to sort of start to interpret differential equations. Have you heard the expression that you should be able to understand a differential equation without solving it? It's a test it's a test that you should try to aspire to. And so we haven't done anything to solve this differential equation, but we still have hooks and tools that we can use to pull out information from it. And that's something that's very useful. Right, it'll guide you in the mathematics that you do, and it may even save you some mathematics. So you should be able to just read these equations, look at the terms over time with experience and with a guide like me. You can start to pull out meaning. Guide. Okay. Sherpa, whatever. Other words for, I don't know, troop leader. Zookeeper? I don't know. All right, where am I? Oh, yes. What's the next thing to do? Somebody help me. What is the next thing to do to this? Hint, it has to do with a long vector identity that you guys did. Excellent. We've been playing with the right-hand side. We can continue to do that for a little bit, but it's time to turn our attention to the left-hand side. And there was a vector identity here that the gradient of the divergence of E, and that's the ugly term, minus the Laplacian of the vector E on that side there. Okay? So, troublesome, ugly, bad. And why is it bad? Why am I so upset with that term? Say it again.
Very difficult to solve.
It's difficult. It makes the whole equation difficult to solve. But why? What about it? If you did the math, there was something unique about these terms versus these terms. Yes, these are the cross terms, the dx dy terms. These are the beautiful diagonal terms of the matrix, and these are the off-diagonal terms, the coupling terms. So remember, I have an equation, a differential equation in time, x, y, and z. And if I've got these cross terms, the del 2 del x squared, del 2 del x del y, I don't know quite how to separate those two variables. So this is what keeps us from being, it keeps the equation from separating. And that's why I really want you to go through and work this out to get a sense of just why that is so troublesome. And you put it exactly correctly. It's the cross terms. Absolutely right. And that keeps you from being able to use, and we're solving a partial differential equation, so I'll tax your memory a little bit, separation of variables. Okay, does everyone remember that phrase from somewhere long back? We'll see what it means again, but there's a separation of variables thing. And in Cartesian coordinates and a handful of other coordinate systems, this Laplacian operator scales separates out very, very nicely. Okay. Well, let's digress a little bit. Whoops. Gradient of the divergence of E. And I want to get that out of there. Okay? I want to be able to cancel this. Well, one way of doing that is to go back to Maxwell's equation and take a look at the divergence of D. Okay? Taking a look at the divergence of D. So, just to point out, I have not used this divergence of D term anywhere else, right? I haven't. Have I done that yet? Didn't I do that once? Yeah. No, I just used a material relationship there. So I haven't done that. I haven't used that information yet. Okay? So I have the divergence of D is equal to rho. Let me be sloppy. And those of you who are really astute will see a contradiction. Okay? But if I say the divergence of E is equal to rho on epsilon, okay? What are you so upset about? Absolutely right. That's my contradiction, right? That's my contradiction. Is I've got. If I do that, I better the heck cancel that term out, and I will. But I want to give you a flavor of something a little bit more sophisticated. Okay? The extent to which we sometimes go to get rid of this term. Well, if that's the case, then the divergence of the gradient of the divergence of E is equal to the gradient of rho over epsilon. And as long as that guy is equal to 0, then this guy will equal 0. And that happens when rho over epsilon is a constant. For a simple material. And if I were to go use this, as you've pointed out, that puts severe restrictions, potentially severe restrictions on P. Okay? So it says that P cannot change with respect to space. Right? So P is not equal to the function of space. But it still potentially could be that P is a function of time. Okay? There's other little things that you can do as well. You can say that it's not a fast function of space, and you can start taking second derivatives with respect to space versus second derivatives versus first derivatives with respect to space, and you could argue that way. Okay? So there's a variety of things that you would do if you had that problem in front of you. Okay? And again, what I'm trying to give you, I could give you this, I will give you the simple way of getting rid of it. Here it is. Keep with simple materials. Ignore P altogether, and it drops out perfectly and nicely. Okay? That's one very, very important learning point from this lecture. But another learning point that's a little bit more sophisticated, and I do know you can handle these, that's why I'm doing it, is that we want to get rid of this term so badly that we will do anything we can, including approximations, to get rid of it. Okay? Once we have that, we have this. And so I have a forcing term from the material, and I have the loss term as well. Okay? I said that my hand-waving definition of a wave equation is a second derivative with respect to space and a second derivative with respect to time. It can have other terms in it, but as long as I have this and this, I've got what we call a wave equation. Okay? And so that's another point of view. When you look at this equation, you identify this guy here as the wave equation, and these are complexities or additional nuances to that wave equation. So another way to look at this differential equation and interpret it without going through the guessing games that you have to solve it. Okay? All right, now, so from the material, from the loss term, let's go back to our simplest case. Okay? Just a very simple case. And what we will have are just the important terms from the wave equation. Do you notice something that I did that I didn't comment on? Yeah. Are you upset about that? You're a little upset about it. And that's okay. You're entitled to be. If I go back to here, and I say epsilon naught chi, and I pull all that into an epsilon there, then this term here becomes an epsilon, and this term never appeared. Okay? And then this becomes rock solid for a constant term. I don't have this term or this term, and so I'm just left with that term. Okay? So I kind of did a roundabout way, but I got to where we would have if we just done the same thing as we did for the magnetic field. Okay? And if you don't like it, we can just set that, you can just have that for free space as well. But it's a little funny to have a mu and not an epsilon. Okay. All right. I'll remind you of something that we looked at a while back. This E has units of what? So that's the volts per meter. And the del squared operator, 1 over meter squared. This guy here is 1 over seconds squared, and then a volts per meter. And they have to have the same units. So this has to have units of seconds squared per meter squared. Right? And so, in fact, 1 over the speed of light in the material is equal to the square root of mu epsilon. Okay? And that's the velocity. We interpret that as the velocity of the waves. Okay? And that's a consequence of any kind of wave equation, whether we do it on a string or water waves or what have you. A wave will move, propagate, and we'll see that. There's a really nice little math lecture that I'll give in the context of a transmission line, where we'll see that again, what that means more physically again. So now I'm just introducing the idea, and we'll put it on better ground later on. Okay. So again, just units tell us something about this as well. Now, this is a vector wave equation. And so that means there's 3 components in there. Okay? So I've chosen to decompose my vector, the direction of my vector. I've chosen the Cartesian coordinates to do that. Okay? I didn't have to. I could have picked another coordinate system, but this is my first choice of coordinates. And if I call that the first choice, what does that suggest? There's more. There's at least a second choice of coordinates. So this is first choice of coordinates, and this is my vector decomposition. Okay? Remember the mathematics that we did way up front on vector fields? Okay. This Laplacian of the vector decomposes del squared EX AX plus del squared EY AY plus del squared EZ AZ. Okay? Does everyone remember that? That's another thing that comes out if you do that vector identity. It's a very nice connection, I think, between the Laplacian of a scalar and a Laplacian of a vector. And del squared E del T squared it gets decomposed like that. So if you think a little bit about the way these vector operators work, these time derivative operators, they break apart nicely and neatly on the components of the vector fields. So this term here is the sum of the EX, the EY, and the EZ. This term here is the sum of the EX, EY, EZ. And I can look at the AX terms together, the AY terms together, and the AZ terms together. And I can set each of those equal to 0 vectorially. X is perpendicular to Y is perpendicular to Z. Perpendicular is another word for independent or orthogonal. And so I set each one of those vector components independently equal to 0. If I do that, I get an equation that looks like that, where I is equal to X or Y or Z. Okay? And one very important thing to point out is I have 3 equations. I have one of these equations for EX, one of these equations for EY, and one of these equations for EZ. So in fact, that last one, I'll just put X, Y, and Z. So I have 3 equations. Okay? Notice that I have the subscript there. And the subscript reminds you to put in the X, the Y, and the Z. Okay? There are many books which will drop that subscript and write that. Okay? And I just want to point out that there's one big difference between this equation and this equation. I'll draw it here. What's the difference? Pardon?
Even the plus and minus.
Well, that's a small. I just took it to the other side.
It's the same.
What's different about this equation from this equation? That's huge. That's a huge difference. But the notation fools you, right? The notation really fools you. This is the vector equation, and it's a vector wave equation, and this is a scalar wave equation. Okay? And let me be even more, kind of push this a little bit more. I squiggle my little lines underneath there to point out a vector, but in a textbook they don't do that. They just have bold face and light face. And so if you think about it, the bold-faced equation took place three pages ago in your textbook. And by the time you get to that, you can't sometimes see the difference between a bold vector and a unbolded scalar. Okay? So I'm harping on this because I think that it's easy to the notation is so cool and neat and nice that it's easy to mess up. It's easy to get a little confused on that. Okay? All right, so what we've done is, just to recap a little bit, we started with Maxwell's wave equations, Maxwell's equations in differential form. These are all vector equations. And so we manipulated, we sought out purposefully a second derivative with respect to space. That allowed us to eliminate one of our terms, our magnetic field, and substitute in an electric field. Okay? We used some material properties. We used we made some restrictions on current and epsilon in order to get rid of this term here. And then we have a simple vector wave equation, the simplest vector wave equation. We need to solve this equation 3 different times. One for the x component, one for the y component, one for the z component. But because of the property of the Laplacian of a vector, in Cartesian coordinates at least, that becomes a very simple separation, a vector decomposition, I should say. And so we can reduce down to a scalar vector equation, 1 for x, 1 for y, and 1 for z. Okay? So the x, y, and z is all in here, and I've separated out into 3 of those. So the trade-off is that I have 3 simpler equations to solve instead of 1 hard equation to solve. Okay? Sorry to belabor that point, but it's important. Okay? In the flow of what we're doing, it's important. Okay. So, our first choice of component of coordinates handled the decomposition of the vector, where the vector is pointing, x, y, and z. Our second choice of coordinates describes the position. And those are 2 independent choices of coordinates. I happen to use Cartesian coordinates for both my first choice and my second choice. Okay? We'll do problems later on where we'll use one for a spherical for one and a Cartesian for the other. Okay? And you'll do problems in the future where you'll choose the 2 coordinate systems to be separate, to be different. I just want to point out that you have that freedom, that you're making 2 consciously different choices for the coordinate system. Okay. So I'll write out the Laplacian of a scalar. D by dx squared plus d by dy squared plus d by dz squared in Cartesian coordinates. And that's what I have. Okay, any questions so far? We okay? Good. All right, now let's just do the x-coordinate first. We have all night long. We'll do the x, the y, and the z. Let's see, I'll draw some axes just to kind of get a little real. I did this right? X to y to z. It's a right-handed coordinate system. I did that right? X to y to z. Good. Now, we want to look for the simplest solution that doesn't break apart. Okay? Where the math doesn't fall apart. Okay? So I want to look for the simplest solution where the math is still supportive of the solution. And what we'll do is we'll say that EX is not a function of EX of X and Y. So that it's only a function, EX of Z and T. Okay? So what we're saying is that in this plane here, there's no change in the electric field. Okay? So if this is the XY plane, if this is the XY plane, the plane of the wall, it can change in Z, and it can change in time, but it can't change as a function of X and Y. So at any instant of time and Z, the same volts per meter must be here, 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 all across that plane. That's what we're saying when we write this equation. We call that a plane wave. Okay? We call that a plane wave. And it's interesting to note, and you'll have to do a little futzing around on your own to figure this out, but if I have the X component, I can choose to keep the Z term or the Y term. But if I have the X component, I have to not equal to this X term here. So that's an absolutely important piece of the plane wave, that EX cannot be a function EX of X. EY cannot be a function EY of Y. EZ cannot be a function of EZ of Z. Okay? In other words, the business end of the surviving equation has to be perpendicular to where the electric field is pointing. Okay? So in this case, the electric field is pointing in the X direction, and at any instant of Z and T, it's the same volts per meter all across this plane. As I clock through in time and keep the Z the same, I can go from 7 volts per meter to 6 volts per meter to 27 volts per meter all along this plane. And in this particular example, the electric field is pointing always to the ceiling. Okay? As I move in Z and freeze time, again, I can allow some variation in the value. The E is still pointing in the X direction to the ceiling, and whatever that value is constant all across that plane at that instant of time. Okay? That's the nature of this solution. Okay? If you happen to guess that EX was equal to EX of X and T, it wouldn't support the whole. Bad things would happen later on in the derivation. Okay? All right. If this is not a function of X and Y, then this term goes to 0, and this term goes to 0, and I'm left with just these two terms. Well, we're now in a position to guess a solution. We've whittled this down enough that we can guess a solution. Incidentally, we're going to solve this equation over the course of the semester in about 5 different ways. Okay? And so we're going to meet it again and again and again, and I'm going to adopt a slightly different approach to solving it. When I do that, you're going to look at this equation from different angles. Okay? And you're probably going to pull together words from a variety of different courses. And you'll see that they all resonate and mean the same thing. Okay? I'll start that process now just by guessing a solution. It's a wave equation that we're solving. We want to solve wave-like equations. What that means is sines and cosines. And I will bow to peer pressure, and I will write those sines as cosines as a complex exponential. Okay? And so the solution that I'd like to write is a sinusoid in time and a sinusoid in z. A complex exponential in time and a complex exponential in t. Now notice that I can rewrite this as e to the I omega t multiplied by e to the plus or minus I kz, right? So this is inherently a separation of variables by the nature of the exponent. Right? Now, if I look at e to the I omega t, what else does that remind you of? Yell it out, I can't hear it. Fourier. Right? E to the I omega t looks like a kernel, Kernal, of a Fourier. So the other way to interpret this guess is that I'm Fourier transforming the equation in time. But since the z is the same form, then I'm also Fourier transforming the z expression in space as well. Okay? So this is also the Fourier transformation of the equation. Okay? You have to chew on that. I want you to think about that a little bit. But one thing I'll point out is, and you know this because you've worked with these equations ad nauseum, right? Is that when you substitute this in, you convert the differential equation to an algebraic equation. Right? It's the same thing as putting in your lumped impedances in your circuit theory. Okay? So if you think about this, both of these are the case, but you don't have to, because according to the basic tenets of solving differential equations, as long as we guess a solution and the solution happens to work, we're okay. Now I want to look at one other thing here. Okay? I have a constant term there, that mu epsilon. And the way I derive this equation, mu would change from material to material, epsilon would change from material to material, so this constant would change from material to material. Okay? So the way I interpret this form here, this is a wave because it's a complex exponential. Euler's expression, cosine of omega t plus I sine of omega t. So this is a wave at a particular frequency. And the way I like to think about that is somebody in charge has dictated that we adopt a particular frequency. Okay? And one example of that is the FCC. If we go to the FCC and we buy bandwidth from the government, they will sell us a piece of bandwidth that's measured in hertz, gigahertz, terahertz, or what have you. So the higher authority, the person in charge, is the FCC that auctions off frequency-based bandwidth. So we will design at a particular frequency in accordance with the FCC, but we have to take into account the nature of different materials. And so this guy here is a mathematical degree of freedom. Okay? Another example comes from nature, where perhaps the spacing of the energy levels in a molecule or an atom dictate that the light that's absorbed or emitted from that atom comes at certain energy quantas which defined by frequency. Okay? So the light out of a laser is always a particular frequency, but when I send that laser through glass or through water or through plastic, something has to change here, and so something has to change here. Because the frequency cannot change, because that's dictated by the energy levels, the quantum states of that particular atom. Okay? Think about TJ's lecture last Monday, the electron on a spring. Certain resonant frequencies, the square root of k over m, the spring constant and the mass. Well, the spring constant was the bond of the atom, and the mass was the reduced mass of the electron and the mass system. And that was a resonant frequency, omega. And that resonant frequency will moving charge. Oops, hang on. I have an equation for that. Moving charge gives rise to light at a particular frequency. Omega equals the square root of k over m. Properties of the atom. And then as that light propagates through glass or through water or through air, something has to adjust, and that's where that guy comes in. That's where that k comes in. Okay? So long sermon about that, but the reason I go into that is because at some point you will get confused over what is always this, what changes and what changes and what doesn't change as you propagate through different materials. Okay? What does the wavelength do, to put it a different way? Okay? All right. Let's see. Well, I've talked a lot, and I think I've done that because after this is just some tedious work. So I need the second derivative with respect to time. And to do that, I need the first derivative with respect to time. I need the second derivative with respect to space. And to do that, I need the first derivative with respect to space. So the first derivative with respect to time is E naught I omega, e to the I omega t plus or minus kz. The second derivative is minus E naught omega squared e to the I omega t plus or minus kz. Let me pause and just point out that the I times an I is a minus 1, right? And so that's where that minus sign comes from. Is I squared is always minus 1. Okay? Definition of the imaginary number. Now notice that I have this plus or minus guy there in my degree of freedom, because I want k to be positive, and I don't know exactly what to do with that, so I'm going to have plus or minus. Well, in fact, let me just kind of point that out to you. Well, hang on. We'll get there. We'll get there. So if I take the derivative with respect to z, things get a little bit more complicated. We have to keep track carefully of our minus signs. Oops, ik, e to the I omega t plus or minus kz. And then if I bring down another ik, I bring down another plus or minus. The plus is always a plus. The minus is always a minus. I'm sorry. The plus times a plus is always a plus. The minus times a minus is a plus. The I is always a minus 1. So whether it's plus or minus, that coefficient will always be a minus sign. Right? E naught k squared e to the I omega t plus or minus kz. So now I have this guy here, and I have this guy here, and I substitute into this term here. The right-hand side of the equation is mu epsilon and d2 dt squared. So I've got a minus sign, I have an e naught, I have an omega squared, I have an e to the I omega t plus or minus kz. The first thing I note is that if I multiply through by e to the minus I omega t plus or minus kz, those exponents go. So the equality holds for all t and z. And that is the definition of solving a differential equation. When I have the left-hand side equal to the right-hand side for all time and space, I have by definition solved the differential equation. Okay? So that's a huge milestone. And after that, it's independent of the value of the electric field. So the result holds for 7 microvolts per meter and 7 megavolts per meter. That's a consequence of the linearity of the equation. And I have now the algebraic equation k squared is equal to mu epsilon omega squared. Omega is always a given, and so we see the k squared adjusts with the material properties. The choice of this complex exponential reduces a differential equation to an algebraic equation, and that's a consequence of the Fourier transform. Okay?